All right, now we're going to talk a little bit about measurement. And measurement is not a simple thing. So I used to do this exercise back when I was teaching is I would ask folks, or even when I was consulting, um, I would have a client come in, we would be talking about their research, and I would ask them, I said, well, let's talk basic stuff here. Let's talk about principle stuff. So I would ask them, have you ever heard of the Stevens scales? And inevitably, 99% of my clients would say, no, I've never heard of the Stevens scales. I'd say, okay, well, have you ever heard of nominal, ordinal, interval, and ratio? They would go, oh, yeah, I know that. I learned that in my first year of graduate school or whatever, undergraduate, whatever. And this was kind of a real sticking point for me because the vast majority of statistical research methods textbooks I ever came across would always talk about nominal, ordinal, interval, ratio, but they would never cite S.S. Stevens as the person who came up with this taxonomy. And it really bothered me because clearly, this was a very, very, very influential, addition to the research literature, the development of these 4 scales of measurement. So anyway, so I have this citation there. I would encourage you to look it up. It's freely available at many places online because it is such an important little article. But anyway, so we're talking about measurement. This is one of the things a lot of people learn as they're coming up through formal educational training is nominal, ordinal, interval, ratio. So nominal is really just naming things with numbers. And one way to think about this is if you're a fan of American football, meaning, NFL, college football, not European football, which of course is soccer. But either way, if you're talking about the numbers that are on jerseys, right, those numbers really don't signify anything other than to identify a particular player. That's really all it is, naming things with numbers. Ordinal goes a little bit beyond that. You're not just naming things with numbers. You're also indicating that the numbers themselves have sequential meaning. And then interval goes a step further beyond that, has those characteristics, but it goes a little further and it says, okay, the distance between each number is equal. And then if you go a step further, more advanced, you have the ratio scale of measurement, where you have all these other characteristics, but you also have a true zero. And zero means there's an absence of value. Now we're going to go into a little more depth in each of these. So here we go, nominal scale. So naming things with numbers, right? So if we think about thoroughbreds, horse racing, the numbers have no purpose other than to identify a particular horse in the race. This can be applied to several types of variables already mentioned using coding, right? So categorical variables such as the state you were born in or your class standing in college can be coded by assigning values or numbers to the value labels, which are the categories, right? So we have there the example 1 equals Alabama, 2 equals Alaska, 50 equals Wyoming. It's also important to note how the numbers or codes or values are assigned, right? So those above, 1 equal Alabama, 2 equal Alaska, could just as easily be reversed, right? So if we think about class standing, you might say 4 equal freshman, 3 equal sophomore, 2 equal junior, 1 equal senior. Well, that could just as easily be reversed where you have 1 equal freshman, first year student, freshman, second year student, sophomore, right? So it could go either way. So again, to kind of switch back to earlier in the presentation when I mentioned code books, right, or manuals, which refer to, a particular data file, it's important to understand how the measurement was done, what the values and value labels or codes mean. Because particularly with a nominal scale, the numbers are somewhat arbitrary. You could just as easily have 444 indicates freshman, or 443 indicates sophomore. The numbers are arbitrary because you're just naming particular things using the numbers. All right, the ordinal scale. When we talk about ordinal scale, we're talking about the added property of sequence, right? The numbers have sequential order. and that order means it has a distinct meaning, right? So with respect to our horses in a horse race, we're talking about finishing order of the horses in the race, or rats in a maze, birth order among siblings, right? Preference ratings. I prefer Diet Coke over Diet Pepsi, and both over Diet Mountain Dew, which I think is rather disgusting, but that's just me. So I would rate my preference as number one, I prefer Diet Coke, right? But as with the nominal scale, someone else could come along and go, well, I really prefer Mountain Dew. So they might flip those numbers, okay? But the order matters. So for that person, they might prefer Mountain Dew. So they might give it a rating of 1, right? So ordinal scale, we're talking about finishing order. The order makes a difference, but it's no different. The difference between 1 and 2 has really no meaning. They're just ordered in a certain way. Finishing order of a race, horses come across the line, they finish the race, first, second, third, fourth. It makes no difference if first and second are separated by 5 seconds and second and third are separated by 4 minutes. Makes no difference. You're just ordering them. All right, the interval scale. Okay, we're naming things with numbers. The order of the numbers matters. Well, with the interval scale, we're adding the additional characteristic of equal intervals between the units. So think of time of day or clock time. The numbers identify objects or points, in this case time. They convey sequence, and they are equally distant from one another. Okay, the interval between 1 o'clock and 2 o'clock is the same as between 4 o'clock and 5 o'clock, except maybe on Fridays, right? Because we can't wait to get out of the office on Fridays. More about that later. Ratio scale of measurement. All right, so the ratio scale has all those other properties, but it also has true 0 point. 0 represents an absence, right? There's no magnitude at 0. So when we think about US pounds of weight or kilograms of weight, 0 indicates no weight. Okay, you cannot have some object or living thing, non-living thing that weighs negative 140 pounds. That's impossible. It doesn't make sense. All right, so and one of the major common examples of this is Kelvin scale of temperature. If you ever deal with anything in astronomy, astronomy not being astrology, but astronomy, when you talk about the temperatures in space and on different planets, 0 degrees Kelvin literally means an absence of temperature. So that's a true ratio scale variable. All right, so as with many, many things in research, there's always caveats and little exceptions and things that we additionally have to think about. So my comment earlier when talking about clock time, right, the distance between 4 and 5 o'clock on Fridays, except on Fridays, right? That was my comment. So this highlights another consideration with respect to measurement. Objective measurement versus subjective measurement, right? Objective, the clock is an example of an objective measurement, right? If it is working correctly, it has no variance when measuring the interval between 4 and 5 o'clock on any day, right? If the clock is working correctly, the interval between 4 o'clock and 5 o'clock should be the same no matter what day, no matter what time of year, right? 1 hour difference, right? That's 360 seconds, et cetera, et cetera. Is that right? No, that's not right. It's like 3,600 seconds. Anyway, subjective measurement is subject to bias, right? As an example, our perception tends to be a little more variable than the clock. So we perceive the distance between 4 and 5 o'clock on Fridays. It's perceived as a little bit longer because we're looking forward to the weekend. We can't wait to get out of the office. Or some of us, I don't know, maybe some of you really like working Friday afternoons. But just as a general experiential example, you can probably sympathize with this. So it's important to keep a perspective and keep a watch out for how bias can creep into measurement. Okay, objective measurement, subjective measurement. Another consideration, and this often comes up in social sciences. And when I say social sciences, I typically talk about things like psychology, sociology, criminology, even. These are sciences that typically deal with human beings. Human beings are incredibly complex and they interact with incredibly complex systems. So when we talk about additional considerations here, I have direct and indirect measurement. So direct measurement is anything that is directly observable or measurable. Sometimes these are called manifest variables. These are typically, but not always, physical things, right? Height, weight, hair length, eye color, skin color, or more precisely, pigmentation. These are things we can measure empirically, okay? Generally, things that are directly measured have less measurement error. They're not going to have zero measurement error because that's almost impossible, but they typically have less measurement error when compared to indirect measurement. These are generally done, or indirect measurement is done with things that are unobservable. Sometimes you'll see latent variables when we're talking about indirect measurement. So for instance, if you talk about love, extroversion, things like that, one of the examples I used to use in class was sadness, right? So, you can measure someone's hair length, someone's weight, someone's height. You can directly measure that. You cannot directly measure someone's sadness. You can't cut open someone's skull, look at their brain and go, oh, there's 5 millimeters of sadness in this person. It doesn't work that way. So sadness would be a latent variable, and it is only possible to measure it indirectly, right? So I have here as an example, I just gave you one of them, obviously, but how do you define sadness, drunkenness, success in college? Are those things easy to measure directly, or can we only measure them indirectly? That brings us to operational definitions. Operational definitions are important because they represent a way of defining something so that it's measured. Okay, you're defining something as it is measured. In other words, you're defining something how it is measured. That's how you're defining it. So sadness here, number of crying episodes in 5 days, self-rating of intensity of crying episodes. Drunkenness, you can measure this a variety of ways. The number of slurred words in a 5-minute conversation. You could also measure it more directly, perhaps, with blood alcohol level. Sort of, yeah. Success in college. There's a variety of ways to measure that. Graduate or not. The number of A's, the grade point average, and so on. So it's important when you're talking about, okay, how are we going to define success in college? Well, let's try to define it the way we would measure it, right? So that's operationally defining something. All right, next we get to common file types and cautions. So with respect to, we're talking about, excuse me, we're talking about kind of raw data and things like this. There are a variety of common electronic file types you will come across. So I just want to talk about some of those common types and talk about their advantages and disadvantages. So here we have the most simplistic form of raw data you're likely to come across, and that is the plain text file. Now, a plain text file has the file extension .txt, and it'll have some type of delimiter to distinguish the columns. So when you open a plain text file, you're going to have a two-dimensional array. Remember what we said, rows and columns. Okay, each row represents a case. Each column represents a variable. The first row is probably going to be a header, which is the variable names, but each column will be delimited or identified by some symbol. And the most common, of course, is the comma. you'll see the file extension CSV is fairly common, comma separated values file, which means each column is separated by a comma. Other popular delimiters are space, right? Space delimited file might have the extension .txt, or you might have a pipeline, which is just up and down line to differentiate the columns, right? So that would be a pipeline delimited file. Might also have the file extension .txt. So the advantages of this file type, the plain text file, are that it's simple. It's going to be a relatively small file size. Of course, it might be huge, but the file itself, relative to other types of file, will be relatively small. And the key advantage is a plain text file will open on anything, any operating system, any type of computer is going to be able to open this file. It doesn't matter how old the operating system is or how old the file is. Any digital computer, any computer will be able to open this type of file without having any errors or things that need to be resolved. The disadvantage of the plain text file is that you're almost always going to have a codebook or manual to explain what's in the data file. So what do the columns mean? What are the values within each column? What do they mean? So on and so forth. All right, so the next type of file type we're going to talk about is the rich text file. And there are a variety of file extensions that fall into the category of rich text. For instance, Excel is the most common, obviously. But what this means is you don't just have basic text in the file, you have some type of formatting or metadata associated with the file. And when I say formatting, think of things like bold, italics, underline, different colors for the fonts. These are kind of rich text aspects or formatting that can go into a file. And so this makes the file slightly larger. And a lot of the common types here, obviously I mentioned Excel. That's probably the most common. I would say probably most, if not all, folks listening to this have some experience with Microsoft Office products, in particular the Excel spreadsheet program, and that's available on or kind of native to Microsoft Windows operating systems. Analogous ones for Apple are the software called Numbers. For Linux, Unix, you would use OpenOffice Calc. They're kind of all the same thing, just different names and designed for different operating systems. Like I said, Excel is extremely popular and can be found with both the old style file extension, which is XLS, and the newer versions, which have the .xlsx extension. And like I mentioned earlier, maybe I didn't, even if you're working on Apple or Mac, you can probably open a Microsoft Excel file. You know, if you're using the Apple product Numbers, you'll be able to open one of the other two and so on. So with Excel and its clones, these are proprietary softwares. Typically, that means, you know, whenever we say proprietary, what we're really saying is someone had to pay for using that software. So the advantages to Excel and its brethren or sistren are that market saturation. It's available everywhere, basically. And the ability to have multiple sheets or spreadsheets within one file or workbook. The other advantage is the point-and-click ease of use, including highlighting different cells, groups of cells, so on, to perform operations. The disadvantages are importing this type of file into software that's not designed for it can be tricky and can cause some headaches. The multiple sheets and additional formatting, all of those benefits also lead to bloated file sizes. So if you take a data file and you look at it in a plain text format, the file is going to be a few kilobytes. And maybe if you open that same file in Excel and it has all this excess formatting, bolding, italics, different colored cells, even though it's got the same information in it, the file is going to be substantially larger in size. Now, this isn't such a big concern these days where you have terabyte hard drives or gigabyte, hundreds of gigabytes hard drives. But if you're dealing with a really large data set, and US Census and some of the things we deal with in the state epidemiological profile, some of the data files that go into that are extremely large. So it becomes cumbersome to do anything with them. But excuse me, that's just something to keep in mind. Like I mentioned earlier, the other disadvantage is that proprietary generally means somebody paid to be able to use this software. Whereas with plain text, you don't have to pay to use that at all. It's ubiquitous, it's everywhere. All right, other common file types, and this category is the stats software stuff. So we're just going to talk about, basically 2, maybe 3 here. So the big 4 are basically SAS, SPSS, and then R and Python. And R and Python I use a little bit interchangeably because they're very, very similar to one another. So SPSS, it's easy to learn, it's point and click, has a graphical user interface, GUI, GUI. It's easy to learn on it. You can point and click your way to do most common tasks in a statistical software program. However, it's very slow to develop, and its official support is not great in terms of getting response. It's owned by IBM. It's fairly expensive. But the data file extension for any data file from SPSS is .sav. And then we have SAS. SPSS is somewhat unique in this realm, and it is unique among the ones listed here on the slide. SPSS being a point-and-click graphical user interface, whereas with SAS, you have to learn the code, the programming language, in order to use it beyond the most simplistic things. So SPSS has a lot more functionality than, SAS has much more functionality than SPSS. And it has a very large and very organized user community. So if you have a question with SAS, you can probably just Google that. You're going to find a host of forums available to find the answer you're looking for in terms of troubleshooting things, or even emailing. SAS user groups, very common. There's often different user groups for institutions, different universities, things like that. You can become a member for free and get answers quickly and learn quicker. But it's also very, very expensive. So the data file extension for SAS is, as you see there, SAS 7 DBAT. And that brings us to R and Python. My favorite, of course, is R. I'm very biased. I'm a zealot for R. I'll say that as my own transparency notice here. Like SAS, you have to learn the code to use it. Same thing with Python. But both of those are freeware. They're open source freeware. So free like the air you breathe. You don't have to pay anything. It'll run on any operating system, which of course SAS does not. So if you're a Mac user, you're probably not a SAS user, because SAS is not really designed to work on Mac or Linux, I think. Or no, it does work on Linux, sorry. Whereas R and Python can run on anything. Very fast development cycles. They're constantly developing, and it's open source. So you can email people associated with a particular package used in R, and you'll probably get a response within 24 hours. But anyway, the data extension, or file extension for the open source programs there are in Python. Typically, there isn't. In fact, there isn't. It's not typically. There isn't a data file extension associated with those because they're not proprietary. They don't have their own data file type. Folks typically use text or CSV, comma separated values data when they're using R and Python. Although, obviously, all of these listed, R, Python, SAS, and SPSS, they can all open the data from each other. It may be a little more difficult, might require a few more clicks, a few more code to go back and forth between them, but you can do that. It's not impossible. All right, last section here, key items 102, other key terms and special considerations. This is very important to remember. Data comes to us with all sorts of human-created errors and idiosyncrasies. If you did not collect the data yourself, chances are very good there will be things which need to be addressed prior to doing any type of analysis. Okay, survey data is notorious for this. Okay, because you're putting out a survey and you have human beings responding to it, and human beings are really, really good at showing you your errors when you develop the survey. And I'm speaking about myself here. Anyone who's ever developed a survey, you know, the first time you start getting data back from that survey, immediately you're going to find things you could have done better because participants, respondents, will find ways to make it difficult to look at that data. So at any rate, so when you have things like open-ended questions where folks can write in an entire paragraph when you were really only expecting 1 or 2 or 3 words, things like that. So the key thing here with the survey is make sure you have pretty tight control over what the response choices are, and don't give respondents the freedom to use a bunch of characters and funny faces and emojis in their responses, because that data is very difficult to analyze later. It can be done. It's a challenge. It's not a game changer, but it can be very difficult. So specifically, we want to highlight 3 common potential problems in the data we typically use. Okay, and these 3 things here are listed: names, proper names for people and places, dates and times, and then also zip codes. So there's some pretty, key things we need to understand about those types of variables, names, dates, times, and zip codes, when we start looking at those things in data. So let's start with the proper names. Okay, so names for people, but also places. These types of names often contain non-letter characters. Think about how many folks you've ever come across who have hyphenated names. How are you going to deal with that hyphen when you see it in a data file? Okay, because it may do all kinds of strange things when you read that data into some software where you're going to analyze the data. So any non-numeric, non-letter character, the software is going to coerce it into something, typically a character string, right? Because it typically sees that and goes, well, this isn't a number, it's not a letter. Let's just pretend it's an alphanumeric letter of some type, character string by default. Other times, some of you have probably heard about ANSI coding. So, if it's not very, very basic, textual thing that's in the data, it might show up in your software as some ridiculous character. Okay, and if you want an example of this, take your average Microsoft Word document and try to open it in a plain text editor. You'll see all these crazy symbols in there. So the point is, whenever you have proper names in a data file, always check the data in plain text first, and especially after importing it into some other software, to make sure that the data is correctly represented electronically without special characters or something that's going to throw you off. And like I mentioned earlier, typically if you have any kind of proper names, particularly with respect to human beings' proper names, you're probably going to want to replace that with unique identifying numbers or letters, I suppose, but it'll save you headaches in the future. So the next thing we're going to talk about is dates and times. Now, it's important to understand that there are actually international standards for date and time expression electronically or digitally. There's an organization, as you can see there, the International Organization for Standardization, ISO, and in particular, 8601, ISO 8601 deals with dates and times. The basic idea of this is, or this ISO, international standard, is to order a date or time from largest unit to smallest unit. Largest unit of time, maybe light years, or maybe just years, down to the smallest unit, seconds, for instance. So with dates, we can have a hyphen or we can have no hyphen according to the standard. But we're going to have 8 digits, or if we're using ordinal only, 7 digits, as you'll see. So as I wrote these slides, the date was September 7th, 2022. So according to the ISO 8601, we should be writing this or expressing it digitally or in a data file as 2022-09 for September -07 for the day, or 2022-0907 without the dashes. The ordinal kind of in parentheses way to do it, and this is not terribly common, but it does occur, is to just have the year and then the number for that day out of the year, right? So 250 would be the 7th of September for the year 2022. So you can see it there. So with respect to time, so that's dates. So with time, it's the same idea. You want the largest unit first down to the smallest unit. So when we format this according to the ISO, we have a capital T, and then we have hour, hour, minute, minute, second, second, right? The extended format just means you have colons between the hours, the minutes, and the seconds. The T can be omitted only when there is no risk of confusion with date expression. So if you look back up to 2022-0907, you might get that confused with some type of time. That's why we use the T in the time expression. So when I wrote this slide, the time was 3:12 p.m. and 27 seconds. How would we write that? We would have a T 1512 or T 15:12. With seconds, you would add on the 27. Midnight is always expressed as 00000, right? So remember the international standards. You can look this up. If you just search, international standard time, you'll see all kinds of stuff on the web about this. But it's important to do that because when you're ordering things or when you're telling a computer, hey, this is a date or this is a time, the computer is going to be able to understand it when you put it in ISO 8601 format. Okay, there's other considerations when you're dealing with computers. So you might come across something called POSIX and some other things, but generally speaking, you're only ever going to have to deal with the ISO 8601 with date and time. So that's the way to do it, best practices. All right, the last thing is zip codes. So, I mean, zip codes, typically with respect to the EPI profile and data sets used in it, we really only need the 5 numbers for US zip codes. We don't need the +4 extension, okay? Because we use these zip codes oftentimes in terms of creating a map, a representation of what's going on in different parts of North Dakota and or surrounding states. And so really we're talking about county level things, and the zip code is only the 5 digits are needed. But with respect to that, it's important to understand that some United States zip codes have 1 or more leading zeros, right? And you see some examples there. Holtzville, New York has a zip code that's 00501. And that's important because Excel in Microsoft's infinite wisdom by default will not show you the leading zeros, because what the software is doing is it's looking at a particular vector or column of values, and there's nothing but numbers in there. That's 5-digit zip codes. And when it gets to Holtzville, New York, it's not thinking, well, this is a representation of a place or a post office. It's thinking, well, this is a number of some sort. I don't need those leading zeros. So you'll just see 501 in Excel. But if you open that same file in a plain text editor, like for instance, Notepad, when you're on Windows, you'll see that it has the leading zeros. The way around that is you can click on that column of data, right click on it, format the cell as zip code, which wasn't always available in early editions of Excel, but now it is, and it'll show the leading zero. Or you can tell it that that column is actually character string, and it'll put whatever's in the data will be displayed then. The other part of this is Canadian zip codes, which are not all numbers, right? Canadian zip codes are 6 alphanumeric characters. We don't really need the hyphen. Sometimes people will put the hyphen in, sometimes not. We don't need a hyphen. We don't need a space. We just want the 6 alphanumeric characters, right? So if we look at Winnipeg, which is obviously a fairly large city, has many zip codes, but you see some of the examples there. So typically you'll have, letter, 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 number, letter, number, or something like that, just to give you an example. The space can be there or not, but it's not necessary. So just trying to standardize some things and to look out for them. All right. Obviously, if we were in person, I would say, are there any questions? And here's some resources you might want to look at, which is my old webpage at University of North Texas, where I was a research consultant for almost 10 years. I have a lot of good stuff on there. Fortunately for me, my friends down there keep that website alive for me. I don't update it or anything, but there's a lot of good information there if you want to take a look. If you do have questions about this presentation, please contact me, and you see my email there. And next time we'll move on to webinar number 2, data considerations in the SEOW context. I have trouble with that. I want to call it so, but at any rate, I guess that's about it. Like I say, if you have questions, please contact me through email. Have a good day or night or morning, wherever you are. And again, thanks for joining. Hope you got something out of this.